Welcome back to part 2 of lecture 4 for MAE170. So in this part, we're going to talk about errors and system types. Sometimes, especially when we're dealing with feedback control systems, we care more about the final value of the error rather than the final value of the output. And let me explain to you what I mean. Let's say that we want to follow a car that travels at constant speed on a road. So the front car represents our desired output, or I should say the position of the car represents the desired output, whereas our car is the actual output. Or again, I should say the position of the back car is the actual output. So the error, even intuitively, it is easy to see that is the distance between the two cars. However, the position of the cars, if the cars, let's say that the front one travels at constant speed, the position will just grow indefinitely, linearly towards infinity. So the desired output is just a ramp. Okay. And also the actual output will also go to infinity. However, the error might not. And in fact, we're interested in catching up with the car in front. So the error, we want the error to go eventually to 0. In other words, we want the final value of the error between the actual and the desired output to go to 0. Sometimes we might have not such a strict requirement. So instead of having the steady state error to be 0, we might let it be less than a certain amount. So we can say that the requirement is that the steady state error is less or equal to a certain requirement. All right, so now we're interested in finding the steady state error. First of all, we have to find the error. In order to do so, let's consider a closed loop control system. As usual, we have our input, that is our desired output, then the actual output that we normally call y of s, a little bit too thick. Here we go. And here we simply have the process. Let's say that we can ignore the control. It doesn't really matter here. We just want to see how or to calculate the error. In fact, what it is usually done before designing an actual controller, you take the process and close the loop and see whether or not the error is driven or the final value of the error is below your requirement. If that is the case, you might even not need a controller. You just have to close the loop and that's it. So this would be the logical step to do before designing a controller. As I said last time, we're gonna consider only unity feedback system. That is, we don't really see a sensor, but the sensor is there. It just means that the sensor is perfect, or the transfer function associated with the sensor is equal to 1. Now, what is the error? The error is the signal coming out of the sum injunction. And by definition, the error is the difference between the input and the measured output. In this case, since the output is measured perfectly, then the error is simply input minus the actual output. In the time domain, we can write it as E of t. I'm using always small letters when we are in the time domain. That is R of t minus Y of t, input minus output. And the steady state value for the error, well, we saw it in part 1. It's just a limit for time that goes to infinity of the function E of t. As simple as that. What about in the S domain? Well, in the S domain, we'll just magically transform all the lowercase letter into capital letters. Of course, that is, we would have to apply the Laplace transform to do so. But if we are in the S domain, we can apply the final value theorem to find the steady state error. That is, we can take the limit for S that goes to 0 of S times E of S. Of course, this is valid if and only if the final value theorem conditions are met. Because if not, you'll have to just go with the time domain definition. All right, so since I told you it's easier to deal with functions in the S domain, let's find the error in the S domain. How to do that? Well, we can, let's say, solve or simplify the block diagram. We've already seen that last time. It's just a repetition of what we already saw, but it's always a good exercise. So E of S, well, we can do it using the rules that we saw last time. So we have one sum injunction and we name the signal after the sum injunction. Then we go backwards and E of S, well, we can use the sum injunction, is equal to R, so plus R minus, and we go backwards until we hit the signal that we know. And the signal is Y of S. So E of S is R minus Y. And that would be the equation. N, in this case, the capital N is equal to 1 because we only have one sum injunction. What about the equation for the output? Well, let's take the output and go backwards. All right, so Y of S is equal to G of S times E of S, which is a signal that we know, so we can stop there. G times E or E times G is the same thing, of course. Now we can substitute the first equation in the second. And by doing so, we find that Y of S, or the output, is equal to R minus Y, everything times G, or Y is equal to R times G minus Y times G. And so Y times 1 plus G of S is equal to RG. And here we have the output. As a function of the transfer function, G, and the input, R. Of course, if we want to take the ratio between Y and R, that is the output over the input, well, that is what we saw and we call T of S, the closed loop transfer function. And that is G over 1 plus G. If you go back to the notes from lecture 3, you'll see that in this case, since GC and GA are equal to 0, G is equal to L, and everything matches. All right, well, here we found again the closed loop transfer function, but we're really looking to finding the error function. We can do that too. It's just I showed you that we can find everything by reducing the block diagram. We can find the output and the closed loop transfer function as well as the error function. So if we want to express the error function, then what we're doing instead, we are substituting 2 into 1, sort of the other way around. So we have that E of S is equal to R minus E times G, or E times 1 plus G is equal to R. So the error is equal to 1 over 1 plus G times R. So the two expressions in the green and in the violet boxes will come up very often, so I suggest you learn them. Now, if we took the ratio between the error and the input, well, that represents the error over input transfer function. It doesn't really have a name, but conceptually, this is what it represents. Okay, so with that being said, what we really were looking for was the error function. Now, what it is commonly done is to rewrite the transfer function of the process, or in this case, the open loop transfer function G of S, in the following manner. We factorize it into, we have a constant term, K, also known as gain. So every time you hear about gain, it's just a constant in the S domain. That's what in control system we're using, gain for constant value, times N of S. So in this case, N of S is not properly the whole numerator, is just a polynomial at the numerator apart from a constant, over, and now we have S to the power of J times D of S. And I'm using this terminology not to confuse you, although it might be a little bit confusing at first, but just because I want to be consistent with your textbook. So by writing G of S in this form, I've factored out all the poles that are at the origin. So this is what S to the power of J represents. So J is an integer or a natural number, can be equal to 0, 1, 2, any number. So it depends on how many poles of G of S at the origin we have. D of S instead is another polynomial that does not contain roots equal to 0. And this is very important to be able to represent G of S in this fashion, because the exponent J is known as the order of the system, or the type, I should say, the system type number. So if we had J equal 2, that would mean that we would have 2 poles of G of S at the origin. Doesn't really matter if we had poles in different places or zeros over here. It doesn't really matter. The number of poles of G of S, okay? Let me repeat it once again. We're talking about the open loop transfer function, whatever is on the upper branch, not the closed loop transfer function T. So the number of poles of the loop function or the open loop transfer function at the origin is the system type number. So if J is equal to 0, then we're dealing with the type 0 system. If J is equal to 1, we have a type 1 system. In this example, J is equal to 2, so we have a type 2 system, and so on and so forth. Once again, the type number is equivalent to the number of poles of G of S that are located at the origin. This is a source of confusion. Sometimes people get confused between open and closed loop transfer function. So the open loop transfer function is what we called L of S in lecture 3. In this case, L is equal to G because we don't have explicitly the transfer function for the actuator and or the controller. We only have G of S. So you have to take a look at the poles of the transfer function on the upper branch of your feedback control system. Using the notation for G of S as K n of S over S to the power of J times D of S, we can rewrite the error to input transfer function, that is E over R. Remember that was 1 over 1 plus G. And so we have that this is equal to 1 over 1 plus K n over S J ds, or that is also equal to S to the power of J D over S to the power of J D plus n of S times K. Or if we simply want the error function in the S domain, well, then we simply have to multiply everything by the input. Here we go. All right, so assuming that this error function in the S domain meets the conditions for the applicability of the final value theorem, here we are assuming that, but you always have to check it. Well, if you can apply indeed the final value theorem, then the steady state error, that is the final value of the error function, is given by the limit for S that goes to 0 of S times capital E of S. So in this fashion, we can also write limit for S that goes to 0 of S times S to the power of J, D of S, and whatever I wrote just a minute ago. Okay, so now that we have a general expression for the steady state error, we can play and we can couple different system types. So we can use different values for J's and different expressions for the input, that is R of S. And we can have an idea of what this steady state error looks like. Does it go to 0? Does it go to a finite value? Does it go to infinity? Well, let's see. Here I'm going to consider just a few inputs and only 3 types of systems. So we're going to consider systems of type 0, type 1, and type 2, and we're going to combine them with an impulsive input that in the S domain is simply equal to 1, with the step input, that is a constant input in the time domain, but in the S domain is equal to 1 over S, a ramp input, a linearly growing input, so R equals to T in the T domain, but in the S domain, that is equal to 1 over S squared. And then we have an acceleration input. Acceleration input is T squared, and in the S domain, this is really 2 over S cubed, but we're just gonna consider 1 over S cubed. It doesn't really matter the factor, it's constant factor. We can always rescale it. It's not gonna make any difference in terms of the nature of the steady state error. So let's start with a type 0. So for type 0, that is J is equal to 0. So G of S simplifies to N times K times S to the power of 0 times D. So we simply have N times K over D. All right, so for the impulsive input, that is for R of S equals to 1, in order to find the steady state error, well, we're gonna refer to this expression, okay? So I'm substituting here J equals 0. And then for each case, I'm going to substitute the proper expression for R of S. So what is R of S in this case is 1. So as S goes to 0, well, everything is driven to 0. S equals 0 does not make D of S nor N of S go to 0. Otherwise, we would have poles or zeros at the origin. And that is already taken care by this term. And we know that for type equals 0, we don't have any pole at the origin. So this limit is simply 0. So a type 0 system, if the input is just an impulse, then the output in the steady state will exactly match the desired output. What about if we change the input? Now we go from an impulsive input to a step input, that is 1 over S. In the S domain. Now you see that this S cancels out with this, and so we're really left with a constant. We have D evaluated at 0 over D evaluated at 0 plus K N evaluated at 0. And this is a finite number. We can also rewrite this number as 1 over 1 plus K times N at 0 and D at 0. So a type 0 system paired with the step input gives us a steady state value that is finite. What if we make the input a little bit more aggressive? Now, instead of having it a constant, we'll have it equal to a ramp. So 1 over S squared. Well, if we do that, this squared goes away with this S, but now if S goes to 0, we have the denominator goes to 0, making ESS, that is the steady state value, infinite. And similarly, if we make the input even more aggressive, that is an acceleration input, Well, we have the same thing. Now at the denominator, we have s squared, so that still goes to infinity. So you see the progression, the steady state error goes from 0 to a finite number and then infinity, and then it will just stay infinity. What if we change and we upgrade the type to 1? Well, in this case, we have that g of s is equal to n of s times k over s times d of s. So I've already set up here the limit, and see the difference is that now we have this s here and here to the power of 1. If we use an impulsive input, that is 1 over here, then the limit is 0, because this goes to 0, this goes to 0, and this goes to 0. If we now have a step input that is 1 over s, let's see what happens. This cancels out with this, but now, due to the fact that we have this extra s at the numerator, this limit will also go to 0. So you see that a type 1, if you want to think about it this way, resists a tougher input. So the steady state error, even to a step input, is equal to 0. What if we upgrade to a ramp? Well, if you caught the logic now, we would expect something finite. Let's see if this is indeed the case. Now, this square cancels with this s, and now the remaining s cancels with this. This term is driven to 0, so we indeed have a constant value that is equal to d evaluated at 0 over k times n evaluated at 0. And this is a finite number once again. If we increase once more the strength of the input, well, now we are left with an s at the denominator driving everything to infinity. So once again, we have a similar progression, 0, and then finite number, and then infinity. And same or similar thing can be said for type 2. I'll leave it for you to see that for an impulsive input, for a step input, and for a ramp input, we have the steady state value for the error that is 0. Whereas for an acceleration input, we're going to have a finite value equal to d at 0 over k times n at 0. Please check it. So we have 3 combinations between types and inputs that would generate a constant steady state error. We have type 0 paired with a step input that gives us a steady state error of 1 over 1 plus kp. In this case, kp is the limit for s that goes to 0 of g of s, that is k times n over d evaluated at 0. And kp is known as the position constant error. Then we have another pair that is type 1 coupled with the ramp input that gives us a steady state error that is constant and equal to 1 over kv, where kv is the limit for s that goes to 0 of s gs, that is k and 0 over d0, and kv is known as the velocity constant error. So sometimes the requirements, instead of being given in the error per se are going to be given in using this constant error. So for instance, if we're dealing with a type 1 system, you might find that the requirement is that the velocity constant error has to be greater than 10, something like that. That means that the steady state error has to be less than 1/10, so less than 0.1. So these things are used. That's why I'm talking about this. Finally, the other couple is type 2 and acceleration input. And in this case, the steady state error is equal to 1/Ka. And of course, now it's just logical, then Ka is known as the acceleration constant error. And Ka is defined as the limit for s that goes to 0 of s squared times gs, which is also equal to k n at 0 and divided by d at 0. So we can also summarize the interactions between type numbers and inputs. So if we have type 0 and the impulse, the steady state error is 0. Type 0 paired with the step input, we have a constant steady state error equal to 1/1 plus kp. If we apply a ramp input, that it becomes infinity and then infinity. Type 1 system paired with the impulse, the steady state error is equal to 0. Same thing with the step input, but with the ramp, it is equal to 1/kv. And then if we increase the strength of the input, the steady state error, in other words, the system cannot catch up with an acceleration input, and the steady state error is equal to infinity. Type 2, well, it can withstand impulse, step, and ramp inputs. So if you think about the car in the previous example, for both impulse, step, and ramp inputs, the car behind can catch up with the car in front eventually. But if the car in front has an acceleration input, so acceleration that is constant, not the velocity that is constant, but an acceleration that is constant, the car behind, it can be represented as a type 2, it will have a steady state error of 1/Ka. That is, it will be at a constant distance, with the car in front, but this distance will be finite. Finally, I just want to point out one thing. As I said earlier, we might have inputs and outputs for which the final value theorem is not applicable. For instance, in the case of the car, the position might go to infinity. So technically, the final value theorem for the functions that represent the input and the output cannot be applied. However, we can still have a finite error. Therefore, the final value theorem is applicable to E of s, the function of the error. And let me give you a quick example of that. Let's say that we have r of t equal t. So we have a ramp input. So r of t clearly goes to infinity as time goes to infinity, because it's just equal to t. We can also take a look at it in the s domain. The transform is 1/s squared. Let's check the conditions for the final value theorem. We have two poles at the origin. So the multiplicity of 0 is 2. Therefore, the final value theorem is not applicable. Now let's say that we have an output function that is equal to 1/s squared times s plus 1. Is the final value theorem applicable for this function? Well, let's take a look at the poles of this function. We have 3 poles. One pole at -1. -1 is different than 0. It is negative real part. So condition 1 is met. But the other 2 poles are equal to 0. So we have a zero pole with multiplicity equal 2. So condition 2 is not met. Therefore, the final value theorem is not applicable for the output either. However, if we take the error function, which is the difference between the input and the output, and let's do that. We have 1 over s squared minus 1 over s squared times s plus 1. So we find that this is equal to s plus 1 minus 1 over s squared times s plus 1. And we are left with 1 over s times s plus 1. So e of s, this new function, which is the error function, can we apply the final value theorem to this function? Well, let's take a look at its poles. We have one pole at -1 and one pole at 0. So what are the non-zero poles? It's just -1. -1 is a negative number, negative real number. So condition number 1 is met. And the other pole is equal to 0, but with the multiplicity equal to 1. So the final value theorem can indeed be applied to the error function, e of s. So we can find the steady state value for the error by using the limit for s that goes to 0 of e of s times s. And let's do that. So we have s times 1 over s times s plus 1. S and s cancel out. So for s that goes to 0, the value, the steady state value of the error is equal to 1. And if you, in fact, plotted the error function in the time domain, this would look like this. And you see that as time goes to infinity, e of t asymptotically approaches the value 1. So keep in mind that even if the input and the output are functions for which the steady state, the final value theorem cannot be applied, the error, that is the difference between the two, might be very well be finite. And therefore, the final value theorem can be applied. So always check your functions, always check the poles, and make sure whether or not you can apply the final value theorem. All right, this is all for today. I will later post the quiz and tomorrow the homework. So I'll see you virtually next time, and have a great weekend and a great 4th of July. And I'll see you next week. Take care.